So I thought I would show you, let's call this math. Let's call this the calculus they won't teach you. I don't know who they are. Calculus off the beaten path. Calculus off the beaten path or something. So this is a little bit of historical account of how things, what happened before we got to what we're about to learn in chapter 5, the slick versions of everything. Okay, this is just for fun. It's not going to be on an exam or something like that. Oh, so I checked a bunch of books about a critical point versus critical value. Everybody says critical point is the x value, and critical value is the y value at a critical point. The exact opposite of what the language suggests, and the exact opposite of what I told you. All right, I'm not going to fight. 10 calculus books all say the same thing. So a critical point means the x value, and a critical value means the y value, the function. Okay, just so we got that clear. But I'll make sure that whenever I ask such a thing, I'm not checking your vocabulary. I mean, in some sense I am, but in this case, I'll be clear about which one I'm referring to. Okay. Good. So where are we? We've been talking about tangents, right? If I have some curve like y equals x squared or whatever, this is like one of the simplest nonlinear functions, then the first thing we did is we figured out how to figure out the equation of a tangent line. Now that method is actually this taking secant lines and getting secant lines to approximate closer and closer, and in the limit getting a tangent line. That's due to Fermat. So Fermat, Pierre de Fermat, is I don't know what to call this, 1630s maybe, French mathematician. He was corresponding with another guy named René Descartes. Maybe you've heard of Descartes. Maybe you've heard of Fermat. I hope you've heard of both of these guys. So they were corresponding around the same time, and Descartes had what we would today consider a crazy way of doing this, but I think it actually slightly predates Fermat. Both of them were slightly off in what the key idea of calculus needs to be. It's not the equation of the tangent line, it's just its slope. We've seen how crucial the slope is to solving all kinds of problems. So they were both interested in working out equations for tangent lines. Of course, equations mean something, well, they mean something once you have the Cartesian plane, which is also an idea floating around at this time that's due to Descartes. So I just want to show you how Descartes did this, because it's kind of fun and crazy. So Descartes was thinking not about secant lines. So Fermat is secant lines approach a tangent line, right? And that's exactly what we've been doing all along. Descartes is thinking about kissing circles. Kissing meaning tangent, like just touching circles. So this is a very wild idea, and it's kind of fun. So let's say we're at this point 1, 1. What Descartes says is, if I know the circle, if I know some magical circle that's centered on the x-axis. Okay, so Descartes' idea is find a magical circle. I mean, magical is not, that's not math. Magical circle that kisses the graph, and has a center and is centered on the x-axis. So if I know this ray, then I know the tangent because it will be perpendicular to it. So his idea is to use this kissing circle to get the tangent line because they will be perpendicular. So that's the idea. Now, how is he going to get a kissing circle? He's going to start, again, it's going to be a limit, but instead of taking limits of secant lines, he's going to take this point 1, and he'll take another point. Let's start with exactly how we started working with secant lines. If we have a circle going through the 2 points 1, 1, and what's this going to be? 2, 4. So what is a circle? Can you figure out the equation of a circle? In other words, find me some center here so that there's a circle through these 2 points centered on the x-axis. How would you do such a thing? So let's say that circle has some equation like x minus a squared plus y minus b squared is equal to r squared, right? That's the equation of a general circle. So far, so good. What does it mean that it's centered on the x-axis? What is this point? Where's the center? Right. It's x comma 0. The way that I've written it, so it's a, the center would be a comma b. In other words, b is equal to 0. So this center is a comma 0. A comma 0. Is that what you said? Yeah. Okay. I'm sorry. I heard x. A comma 0. Okay. In other words, b, we know what b is. B is 0. Does that make sense? So can we figure out, we don't need to make this into a quiz, but it's something very simple. Can we figure out, so our goal is to find a and r so that this equation is satisfied by the 2 points, right? This is the equation. Any value of x and y that satisfies this relationship will be at distance r away from the point a comma 0. So can we find 2 points that satisfy this? Well, it's very simple. You plug in the 2 points. Let's set x equal to 1 so that this contains, let me finish the sentence, contains the 2 points 1, 1 and 2, 4. So if I set x equal to 1, that's 1 minus a squared plus, and y is equal to 1, that's 1 squared equals r squared. And our other equation is 2 minus a squared plus 4 squared equals r squared. You see that these are the 2 equations? These are 2 equations and 2 unknowns, but they're very complicated equations. There's squares, and it's not linear. It's not something nice like when you're solving for secant lines. It looks bad so far, right? But Descartes observes some magic. So what's the magic? Do you see it already? Yeah, well, first of all, exactly. First of all, just observe that r squared is r squared. So we can immediately remove r and just have an equation in the a's. And let's see what the equation in the a's is. So if I multiply this out, I get 1 minus 2a plus a squared. That's this thing, plus 1 is equal to, here's my new equation, is equal to 4 minus 4a plus a squared plus 16. Does everybody see that? And what do you notice about this? What is it? You notice anything? We're trying to solve for a. It's going to be a very hard quadratic. Other than Raghav? Yusuf? A squared. Yes, exactly. The a squareds are there on both sides. It is linear. That's Descartes' kind of great insight here, that when you're solving what seems like a very complicated set of equations, actually it boils down to something very rather simple. And so let's see, if I put the 4a to the other side, I have a 4a. Okay, so here's one thing. I had a little discussion with some of you. I tend to do algebra quickly, and I think that confuses some people. So let me mark. How do I mark something? I'll mark an alj. I'll just put a star. Star means this is just algebra. So if you don't want to do the algebra as fast as I do, just check this on your own at home. Okay, but I'm just going to move this 4a to that side. There's a negative 2a. That's a 2a on this side. On the other side, I have 4 plus 16. That's 20. And there's a 2 on this side, which I'll move over. So 20 minus 16 is 18. So I think I'm getting a equals 9. And if a is equal to 9, now I can put that back into, for example, this equation. If a is equal to 9, 1 minus 9 is negative 8 squared is 64. Plus 1 squared is r squared. So r is square root of 65. Okay, does that make sense? And let's check. So what's our equation? We have one equation that's y equals x squared. We have another equation which is x minus 9 squared plus y minus nothing, just y squared, is equal to square root of 65 squared. So let me pull up Desmos. Y equals x squared. There's that parabola that we all know and love. And what was the equation? X minus a was 9. the center is going to be on the x-axis, so there's a y squared, is equal to square root of 65 squared. And look at that, it passes through the points 1, 1, and 2, 4, and it's a circle centered on the x-axis. Okay? That was the first thing. The first thing we did, I'm sort of reminding you how we came up with the formula for tangent lines. We took a secant line, and now instead of a secant line, we're taking a secant circle, a circle that crosses through 2 points. And what did we do with the secant line once we could do it at 2 points? We made that second point a variable, and we started pulling that point closer and closer to the point 1, 1. And that in the limit gave us a secant line approaching a tangent line. Same thing is going to happen here. So can we do this in general? Let's do exactly the same thing. Again, want a circle through. So here's our y equals x squared. Here's the point 1, 1. And now I'll take some other point. Instead of 2, I'll take some variable c. That's my nearby point. This is the point c, c squared, because it's the graph of y equals x squared. Exactly. And now I want to try to figure out some point on the x-axis. So this is the point a, 0, which passes through both of these. Okay. Let's do it together. I won't give you a quiz today. It's Thanksgiving. Let's have a nice. So the equation again is the same equation, x minus a squared plus y squared is equal to r squared. We have one point on the graph, which is 1 minus a squared, this point here, plus 1 squared is equal to r squared. And our other point is, it is whatever it is, c minus a squared plus c squared squared. That's c to the 4th, everybody see that? Is equal to r squared. We can set these two equal to each other, because the r squareds are equal. If I multiply this out, so let's multiply everything out, I get a 1 minus 2a plus a squared. That's that, plus 1 is supposed to equal c squared minus 2ca plus a squared plus c to the 4th. Did everybody get that? Does that make sense? Again, the a squareds cancel on both sides. Descartes' great observation is you get something linear. I'll move the 2ca to this side. So what do I have in front of a? I have 2c minus 2. Is that right? Hopefully you guys are following along, checking this. And now I'll move, what do I get on the other side? I have a c to the 4th. I have a c squared. And there's a 2 from here, 1 plus 1, that I'll move to the other side, minus 2. So a is equal to c to the 4th plus c squared minus 2 over 2c minus 2. Okay, and then I can put that back in for here and work out what r squared is. So r squared is 1 minus, well, I'll just leave, I mean, there's kind of no point in simplifying this. R squared is just this. This is some nasty thing. Should we find out if that equation was right? Let's try it. So we had c. C is going to be, how do I make this into a, okay, let me just try something. I think I can do x minus c. Yes, add a slider for c. Good. Okay, so I have now a value for c. And a, the equation is x minus a squared plus y squared is equal to r squared. A is this thing. So x minus something complicated. C to the 4th plus c squared minus 2 over 2c minus 2. Yeah, did I type that in right? So that whole thing squared plus y squared is equal to r squared. Now r squared, again, is 1 minus that annoying thing squared plus 1. Let me do the, yeah, so 1 minus, oh, this annoying thing, that's this. That's that. That's a, 1 minus a, okay, all squared plus 1. Did I get an equation? Oh, because c is equal to 1, so I'm not going to get an equation. Okay, so check this out. look at what we've done. As we move the slider along, for any value of c is 1.4. This point where they touch, one of the points is 1, 1. The other point is 1.4 plus the square of 14 is 196. So 1.96. You see what we've done? We made a general version of what we did when c is equal to 2. We found a circle that passes through that point and touches this parabola, bless you, at the prescribed value c. C is 1.7. Here's the 1.7. You guys see what's going on? Okay, so now all I have to do is take the limit as c goes to 1. Of course, it's going to disappear when c goes to 1 because it can't divide by 0. But if I zoom this in, let's see, 0.9. 0.9 up to 1.1 with a step of 0.01, something like that. So now let's zoom into this. Okay, you see these green circles? You see how the green circles are getting closer and closer to being exactly tangent? And it will be exactly tangent when c is equal to 1, but then Desmos says I'm dividing by 0 and I can't do that. Okay, so that's exactly the limit we want to try to figure out. Beautiful, but we know how to do that. What happens to A? So now we want to understand what happens to A. Finally, we want to take the limit as c goes to 1 of this family of circles, which means of A. So what's the limit of A as c goes to 1? Well, remember what A is. This is the limit as c goes to 1. Everybody see what we're doing? We have this number c on the graph of y equals x squared, and we're pulling c closer and closer to 1. And we have this family of circles, and eventually when c is exactly in the limit as c approaches 1, we'll get the circle that exactly kisses the curve. So I have c to the 4th plus c squared minus 2 on top. On bottom, I have 2c minus 2. Oh, this is going to be annoying. We have to factor that by that. And let's check, by the way, when c is equal to 1, this is 1 plus 1 minus 2, that's 0. So the numerator is vanishing, but the denominator is also vanishing. We have L'Hopital. Oh, we don't have to do anything complicated. We have L'Hopital, right? So this is 0 over 0 form. This goes to 0, this goes to 0. So we'll use L'Hopital. This is the limit as c goes to 1. What's this? 4c cubed. Of course, Descartes did not have L'Hopital. L'Hopital is 100 years later, just for reference. Not 180, whatever. 2c on top. On the bottom, I just get a 2. So what happens? Did I do that right? 6 over 2 is 3. So c is equal to 3. That means that circle, that optimal circle, should be centered. Here's the point 1, 1. It should be centered at the point 3, 0. And here's the point 1, 1. So if I make a circle, and what's this distance? This distance is root 5. Distance is root 5 between those points. And so if I draw the circle, finally, if I draw the circle, x minus 3 squared plus y squared is equal to root 5 squared, which is 5. That circle is the kissing circle to the curve. Now, what is this slope? What is the slope of this line? The rise from here to here is -1. The run is 2. So the perpendicular slope, the slope that's going to be perpendicular to this perfect circle, is the negative reciprocal, which is 2. And by the way, the derivative of x squared is 2x. And if we evaluate this at x equals 1, we indeed get the same value 2. We could have just done power rule. Of course, all of those rules, all those things that we're talking about are 80 years after what Descartes is doing.
So the whole big circle just so that you get the slope of the line, or did he use the circle as the
No, he used all that to get the slope of the tangent line. Hey, it looks dumb to you, right? Because we know the better way to do it now. that better way has been developed over centuries to make it so that 18-year-old kids can understand this material. This was the frontier of mathematical research at the time. Okay, things got simplified, things got vastly simplified to the form that we have it today. But this is what it looked like back then. All right, so Descartes and Fermat are going back and forth. And Descartes says, look at how elegant my method is. It's so beautiful. It gives you these tangent circles. By the way, the tangent circles give you something more. They tell you about the curvature, which we're not going to get into what curvature means. Basically, the curvature, yeah, let me not get into what curvature means. Yeah. Anyway, yeah, here I go. The curvature is if you're driving around the road, how hard you have to turn the wheel in order to stay on the road. So the harder you have to turn, the more curvature there is. So it's about approximating a curve by a kissing circle again. Now, not necessarily one that's on the x-axis. So it's a slightly different phenomenon. Anyway, Descartes was very interested in these things. He did a lot of things with circles, this great geometry. He introduced this coordinate axis, although not, again, in a much more complicated way than what we have now. But these guys were thinking about this stuff. I just want to make the point that calculus, everybody says calculus started with Newton and Leibniz. First of all, it started 200 years before with an Indian named Madhava who knew a lot of the things that we're talking about. And it started 2,000 years before with a guy named Archimedes. So the next thing that we're headed to, this is sort of the bridge from derivatives to area, which we'll eventually know as integrals. That's where we're headed. But area really started with Archimedes. And what Archimedes, so this is the ancient Greek Archimedes. This is like 250-ish BC. What he figures out, again, let's look at our favorite parabola. He would never draw a parabola on a coordinate axis. That's, of course, much later invention. What happened? There we go. I don't know what I pressed. Here's our y equals x squared. He could tell you the area. So if I look at the graph of y equals x, okay, here's y equals x, and I say, okay, the point 1, 1 is on this curve, and what is the area under the curve? The area under this curve. Area under the curve. Yeah, it's a triangle, right? Y equals x from 0, 0 to 1, 1 is exactly 1/2 base times height. So this area is a half, right? The base is 1, the height is 1. This area is a half. Nothing to it. Archimedes, 2,000 years ago, was able to figure out the area under this parabola. What he really did is he figured out the area over the parabola. And you can subtract a half from that to work out what this area is. And the way that his solution is, we're not going to go through his solution, it's purely geometric. It's absolutely brilliant. And it's to say, okay, somewhere between these 2 points is a curve, is a tangent line that exactly matches, that's parallel to this line. Does that smell like anything? The mean value theorem. The mean value theorem. Archimedes used the mean value theorem 2,000 years before it was proved. I mean, it's intuitive, it makes intuitive sense. So he says, look at this curve. Somewhere, I mean, he proved that this curve exists, and he showed how to construct it and so on. Somewhere there's this point. By the way, where is that point on this curve? What's this slope? This slope is 1. And so where is the point that has exactly that slope? So if I look at the derivative, again, the derivative of x squared is 2x. When is that slope equal to 1? When x is a half, right? So right here at x equals a half, so this point is actually exactly 1/2 comma, I guess x squared 1/4. So the point 1/2 1/4 has a slope that is exactly the same as the slope from here to here. And what Archimedes showed is that if you take this triangle, this is getting a little hard to see. Let me make a new, let me color it. Go away. Let me color this. If you take this triangle from here to here to here, you see that? Straight lines. So triangles, it's easy to work out areas of triangles. So he said that this area area of this triangle from 0, 0 to a half, a quarter, a half, a quarter to 1, 1. If you take that area and you multiply it by 4/3, this magic number 4/3, you get exactly the area under this parabola. Area under the parabola. Okay, 2,000 years ago, he managed to do this. Now I want to show you how Fermat rediscovered or discovered a new method. It really is a genuinely new method. Archimedes gave several. Let me not tell you how Archimedes did it. It'll take us too far off course. It's a purely geometric argument. We're not going to learn too much here from it. There's lots of YouTube videos and expositions. Just Google how Archimedes did this. This is called the quadrature of the quadrature. Q-U-A-D-R-A-T-U-R. What does quadrature mean? Quadrature of the parabola. What is it? Anybody know? Quadrature? It means to square something. A quad is like a square. So this means to square. What does it mean? Like, oh, he's so square. He's lame, right? He's boring. You can easily predict him. You can make sense. All right. So something that's, or I can't square that. I don't, that's an old fashioned, you don't really hear that much anymore. Like that doesn't square with this other thing you said, right? I can't make sense of it. So squaring is how you make sense of something. This goes back to the times of, everybody's taxed all the time, but the king would say, what's the area of what's your plot of land so that I can tax you? I have to figure out your area. And to figure out an area is to square it, to turn it into an area of a known quantity. Okay, so quadrature is to work out the squaring of something, is to make sense of it. Squaring is literally figure out area in terms of a square. So give me a square that has exactly the same area as the object that you are studying. Okay. Anyway, so this is called the quadrature of the parabola due to Archimedes, and he worked this thing out. And you can this area, if I recall correctly, this area was going to come out to 1/8. I'll leave it to you. This is a very simple exercise to work out the area of this triangle. It's I believe 1/8. Let's see if that's right. 1/8 times 4/3 is 1/3. 1/6. 1/6. So this area is 1/6. So what's the area below a parabola? Therefore, the area under a parabola, this area is 1/6. The whole triangle has area 1/2. So the area under the parabola, 1/2 minus 1/6, 1/3. Okay. Let me show you how Fermat figured out areas of this form. In fact, he could do any power. This is he gave a very powerful method, which is not a method that works for general functions. But here's Fermat's method for area. Fermat's method for area under something like y equals x to the n. Let's do it x to the, give me a nice small number, 4. 5. What do you like? 4. Let's just do 4. 5. Okay, let's do x to the 5. Okay, so x to the 5 looks like this. Here's 0, 0. 0, 0. Here's 1, 1. 1 to the 5th is still 1. And I want to know the area under the graph of x to the 5. This is y equals x to the 5. Well beyond the comprehension of the kinds of things that Archimedes could have understood. Okay, they didn't think about these relationships. To Archimedes, a parabola is a slice through a cone. You guys know about this? A parabola is a conic section. If you take a cone and you cut it, you see how there's a slope to this. There's like, if you think about an ice cream cone, you take a piece of paper up to that ice cream cone. That's a way of being tangent to the cone. Well, if I take a sword and I cut the cone parallel to that, so if the plane that I'm cutting here is a plane that's parallel to this edge, then this curve is a parabola. That's why it's parallel. Para is for parallel. So this is a plane. This is called a parabola. The parabola, which is here, is a conic section, which means you cut a cone by a plane, and this plane is parallel to the tangent plane to the cone. To the cone. Anyway, so that's how Archimedes is thinking about parabolas. Actually, this viewpoint of parabolas is due to Apollonius. I'll put his name here as well. Right, some ancient Greek. Let's get to something a little bit more modern. So we're going from 300 BC up to 1630s. Okay, 17th century. Still a couple of decades before Newton. Okay, so what's Fermat's method for the area under a curve like this? Here's what he does. He says, you know how we took this number C and we pulled C closer and closer to 1? So he's going to take a number, we can call it C. Let's call it C. He says fix some value C less than 1. Now what happens to, so let's say here's C. So this is the point C comma C to the 5th. You know what? It'll be slightly easier if we use the 4th power. Doesn't matter. It'll be ever so slightly easier if we use the 4th power, which goes like that instead of like that. Anyway, it's a cosmetic thing, but I think you'll see how you can do any power you want if you can do the 4th, the 5th, anything like that. So here's the point C comma C to the 4th. If we fix this value, okay, so now we have this point. Where is C squared? C squared is bigger than C, right? C is less than 1. So if you multiply C by something less than 1, you get something smaller than C. C squared is actually smaller than C. C squared is over here. And what is this point? C squared, comma, C squared to the 4th, C to the 8th. Okay? And then there's this other point, C cubed. Now they're not equally spaced. I'm sort of not doing a very good job of drawing this. Let me try a better picture. So here's the graph of y equals x to the 4th, 5th, 4th, let's say 4th. Here's 1, 1, 1. So if this is C, then C squared is a little closer, and C cubed is a little closer, and C to the 4th is a little closer still. So this is C squared, C cubed, C to the 4th. And here are all these values. This height is C to the 4th. This height is C to the 8th. This height is C to the I have C cubed to the 4th, C to the 12th, and this height is C to the 16th. Okay. And then what he does is he says, well, this total area underneath the curve, so the area under the curve is at least the area of all of these little rectangles. I take this rectangle, I take that rectangle, I take that rectangle, I take that rectangle, and he starts adding them all up. What? I know what we're getting. You know what we're getting to. Well, this is a different treatment than what we're going to cover. We're going to cover the standard, sort of synthesized treatment that like has been cleaned up for your enjoyment, amusement. I don't know what, but this is sort of the raw. This is like to Hader's question. This is, Descartes was doing something clunky. Fermat is doing something a little bit clunky here, but he gets the answer, and he gets it long before Newton. So what is this? What's the base of this rectangle? 1 minus C, exactly, Yusuf. And what's the height? C to the 4th. Okay, how about the next rectangle? What's its base? C minus C squared. And what's its height? C to the 8th. What's the next one? C squared minus C cubed. And its height? C to the 12th. And the next one? C cubed minus C to the 4th with a height of C to the 16th, and so on forever. Okay? C minus C squared, we can factor out a C from this. Let's factor out a C. That's C times 1 minus C. C squared minus C cubed. we can factor out c squared. Let's pull out a c squared. That's c squared times 1 minus c. C cubed minus c to the fourth is c cubed times 1 minus c. Okay, and so on. So we can pull out a 1 minus c from all of these. There's a 1 minus c everywhere. There's also a c to the fourth everywhere. This is a c to the 9. This is a c to the 14. This is a c to the 19. Let's pull out a c to the fourth. What's left? This leaves 1. We've pulled everything out. This leaves, there was a c to the 9. I pulled out 4 of them. C to the 5. How about this one? C to the 14. C to the 10. And here, c to the 19. I pulled out 4 of them. C to the 15 and c to the 20, and so on forever. So far, so good? Everybody with me? Now, do you guys know how to sum a geometric series? Some of you do, some of you don't. Okay, so let's talk about that. If I have 1 plus r squared plus r cubed plus r to the fourth plus r to the fifth and so on forever, I take this quantity. If I multiply this by 1 minus r, let's see what happens. So I'm going to multiply everybody by 1. That's 1 plus r squared plus r cubed and so on. I'm also going to multiply everybody by negative r. So what's 1 times negative r? Negative r. And how about r times negative r? Negative r squared and negative r cubed and so on. So they all telescope, they all cancel out, except the 1. So this product's equal to 1. So the geometric series 1 plus r squared plus r cubed and so on forever is 1 over 1 minus r, if I divide both sides by 1 minus r. Everybody see that? Does that make sense? So what's 1 plus 2 plus 4 plus 8 plus 16 and so on forever? That's 1 over 1 minus 2. 1 minus 2 is negative 1, so that's negative 1. That doesn't make sense. Of course, this only makes sense if r is, if this has to converge, r has to be less than 1 in absolute value. In fact, there is a way to make sense of this, but it requires jumping over the value r equals 1 to move to the value r equals 2. So when you get to complex analysis, you'll learn how to jump over bad real values. So this can be made sense of. So this, of course, is not really an equal sign, but this is a topic in complex analysis. When you learn about complex numbers, you'll see how to make sense of formulas like this. Anyway, never mind. So we know this. And the area that we are looking at, let me grab it, is this. No, not zoom. Okay, let's try that. I don't know why that happened. There we go. And paste. Okay, let's go over here. So here's the area. 1 minus this, there was a c to the fourth. So the area that we're interested in, the area under that curve, is at least 1 minus c times c to the fourth times all of this stuff, right? And what am I going to put? What is r in this setting? C to the fifth. So this sum is 1 minus c times c to the fourth. By the way, is c less than 1? Yes, c is less than 1. We're treating c. So c is less than 1. So we're okay to apply this formula. And what does this whole thing sum to? 1 over 1 minus c to the fifth. C to the fifth. I can multiply all of this out, and I get a c to the fourth minus a c to the fifth over 1 minus c to the fifth. There's a simpler way to do it. I'll show you in a minute. But anyway, so what do we have? We have this area. And for any value of c, now think about what happens as c gets closer and closer to 1. As c gets closer and closer to 1, these rectangles get thinner and thinner. And they become a better and better approximation, possibly, to this area. But for any value of c less than 1, we fixed any c less than 1. this expression is a lower bound for the area. So of course, in the limit as c goes to 1, we still have a lower bound for the area. So the area is at least, this is true for any value of c, it's at least the limit as c goes to 1 from below of this expression, c to the 4th minus c to the 5th over 1 minus c to the 5th. Oh, that's 0 over 0. We can use L'Hopital if we like. This is the limit as c goes to 1. You don't actually need L'Hopital, but it's an excuse to do it, to remind you of it. So what's the derivative here? 4c cubed minus 5c to the 4th over negative 5c to the 4th. And what happens to that as c goes to 1? The denominator is negative 5, so it's no longer indeterminate. The numerator is negative 1. Negative 1 over negative 5, 1/5. So this area, whatever it is, it's at least 1/5. Everybody see that? All right, but that's a lower bound, Dan. The 1 minus c to the 5th here was putting in our formula for a geometric series. I'm going to use that on this expression. So 1 minus, we recognize that r is c to the 5th. We use this formula with r being c to the 5th. Does that make sense? So that's where we got from there to there.
So r to the 1 plus r to the 5th plus r to the 10th would be 1 minus or 1 over 1 minus r to the 5th.
Exactly. We're applying this formula with, we set r equal to c to the 5th. This is true for any value of r, as long as r is less than 1. C is less than 1, c to the 5th is also less than 1. So there's no problem putting this in here. Okay, Yusuf. We are computing the area under the equation y equals x to the 4th. In the process of computing this area, we got this sequence. So some algebra later got us to these 5ths and 10ths and 15ths and so on. Okay, so far so good. We're not done. That's just a lower bound. That's not good enough. We might be missing some stuff. Let's see if we can get an upper bound. So Fermat continues. He looks again at this same graph with our 1 comma 1 here and so this is 1 and c comma c to the 4th and c squared comma c to the 8th and c cubed comma c to the 12th and so on, not drawn to scale. And he says, wait a second, this rectangle plus this rectangle plus that rectangle plus that rectangle plus that rectangle are all going to overcount the area, right? So the area, whatever the true area is, it's at most these areas, the sum of all these areas. Does that make sense? What's the base? This is 1 minus c. What's the height? 1. This height is 1. Everybody see that? What's the next one? This is from c to c squared. C minus c squared. What's the height? C to the 4th plus c squared minus c cubed with a height of c to the 8th plus and so on. Okay. Again, we can pull out a 1 minus c from everything. This expression leaves a 1. When I pull out 1 minus c, there's a c and a c to the 4th. C to the 5th. Here, I pull out a c squared to leave a 1 minus c. C squared and c to the 8th, c to the 10th. That's the only reason I wanted to do the 4th power. So you can recognize the 5th and the 10th and the 15th and the 20th and so on. Okay, so that continues just like before. Just like before, we would get a 1 minus c, and this all sums to 1 minus c to the 5th. By the way, 1 minus c to the 5th factors as 1 minus c times 1 plus c squared plus c cubed plus c to the 4th. If you multiply all this out, exactly in the same way, you get a telescoping sequence, except there's a first and last term remaining. That's what Fermat did. He didn't know L'Hopital's rule, obviously. So this expression is equal to 1 over 1 plus c squared plus c cubed plus c to the 4th, What happens to this as c goes to 1? As c goes to 1 from below, what happens to this expression? 1/5. There's 5 terms, each of them is going to 1. So we have a lower bound for the area, which is 1/5. We have an upper bound for the area, which is 1/5. We've squeezed the area. Okay, so the area, so this is what Fermat understands. Fermat tells us that the area under the graph of y equals x to the 4th from 0 to 1, from x equals 0 to x equals 1, is 1/5. Exactly. We said the area can't be less than 1/5, and the area can't be more than 1/5. It's got no other choice. Does that make sense? So this was all well before Newton, Leibniz, and those guys. Here's the, so by the way, so just to put it here, Archimedes showed that the area under the graph of y equals x squared, this isn't how he would have said it, but effectively he showed is from 0 to 1, from 0 to 1, from 0 to 1 is, do you guys remember? 1/3. We had it right here. Where's that 1/3? Archimedes. Yes. Where is it? A 6. There it is. A 1/3. 1/3. This 1/3. Fermat works out the other areas. He notices a pattern. So in general, the area under y equals x to the n from x equals 0 to x equals 1 is 1 over n plus 1. And then a guy named Isaac Barrow. Anybody heard of Isaac Barrow? He was Newton's teacher. Newton's teacher. It's not clear how much Newton learned from Isaac Barrow, but he managed to push this method. Why stop at 1, 1? If you take the function y equals x to the n out to any constant c, you get a similar computation. So the area, he works out that the area under y equals x to the n from x equals 0 up to x equals c turns out to be this 1 over n plus 1, which would be the case if c is equal to 1, with a factor of c to the n plus 1. That's if c is greater than 0, for any value of c greater than 0. Doesn't have to be bigger than 1, could be less than 1. For any constant c, that's the area that he works out just by following Fermat. You can do this. Does that smell like anything? Say it again, Jenny. There's a trapezoid method. We're going to talk about all the, yeah, that's exactly what the whole next chapter is about, the now traditional way to do these things. What I'm showing you is the things that for some reason aren't in textbooks because they're historical things, they're clunky ways that people used to do things. Clunky, but actually extremely clever and extremely simple. Do you notice anything strange about this expression? Does it smell like anything? That's the antiderivative. Exactly. This, if you notice, the antiderivative of x to the n is x to the n plus 1 over n plus 1 plus c for any c, right? Plus, let me call it k so we don't confuse it with this c. Okay, so they notice these kinds of relationships. This thing that we talked about on the very first class, that differentiation and area are opposites. Finding the area under a curve and finding a tangent line are somehow opposite to one another. And it's not until Newton. So, by the way, this is like 1665-ish. He's supposed to be at Cambridge. He's had a couple of years at Cambridge, and then he gets sent home because he's quarantined because of the Black Plague outbreak in London that kills a quarter of London's population. So he's home from quarantine. He's home from Cambridge, where he's supposed to be studying. He's like 20 years old, 22, something like this. 22-year-old Newton. So if you know some seniors, well, you know, you can ask them what they did on their quarantine. He generalizes this. He's aware that there's some relationship like this already. Okay, but he shows for general functions, he basically invents differential calculus, integral calculus, which is what that's the next. So these areas are going to be called integrals. That word is not from Newton. He calls these things fluxions, how things fluctuate. What's that? That's a cool name. Yeah. So do you guys take AP fluxions in high school? The reason you didn't take AP fluxions because Newton doesn't tell anybody what he's doing. He keeps this in his desk drawer until like the 1690s. Meanwhile, a guy named Gottfried Wilhelm Leibniz, TZ or Z? I think it's TZ. Leibniz, in 1670s, I'm gonna make up a number, 1674, something like this, starts thinking about similar things. Now he is corresponding with Newton, and he's also been shown some of Newton's documents that were not prepared for publication. My own hypothesis, I don't know if we've talked about this. My own hypothesis is that Newton isn't comfortable with the theory of limits, these indefinite 0 over 0 things. The way that he writes about them is very fluffy. Oh, you take the values after they've vanished, not when they're vanishing. Like it doesn't make any sense. He doesn't really have a foundation for the calculus, which won't come for another 200 years. But Leibniz has no qualms about this. It's kind of strange because he's a philosopher, like Descartes. Is it L-I-E? Can somebody Google this for me? It'll be so embarrassing. L-E-I or L-I-E? I feel like it's L-I-E. Anyway, so Leibniz has his own investigations into calculus, rediscovers, or as far as he's concerned, he says discovers the calculus, and he publishes it in the 1680s. Publishes in the 1680s, and he starts teaching it to people like Bernoulli. So Johann Bernoulli was one of the first AP Calc students. Johann Bernoulli and his brother Jakob. There's a whole family. There's Daniel Bernoulli, who was a friend of Euler. So the Bernoullis, there's a Bernoulli family in Basel, in Switzerland. Start learning calculus from Leibniz and from Leibniz's writings, which have been around since the mid-1680s. They teach it to a guy named Leonhard Euler. If you read any Euler textbook, it looks just like modern mathematics. Euler was so popular with his textbooks on calculus were so popular, he standardized all of the symbols that we use, all of the methods that we use to write things. Newton will look a little bit familiar. Leibniz won't look familiar at all. Newton will use the dot notation instead of a derivative. This ddx notation is Leibniz, ddx. Newton will say x dot. So that's how x is changing with respect to time. And so if you want the fifth derivative, you got to go x dot 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 dot. Something like this, as opposed to d5 over x to the 5. Okay, so there's a lot of reasons we don't have AP fluxions. We have AP calculus. That word comes from Leibniz. Of course, neither of them is aware that Madhava had done a lot of these things 200 years before. But they get into a big fight. So Newton finally publishes in like the 1690s. In some sense, his calculus doesn't really come out until 1710s. I mean, he's much more well known at this point for his Principia of mathematics, which is the laws of motion, where he's explaining what, so he uses calculus to derive laws of motion, to derive theorems from the laws of motion. So this is a Principia. The Principia comes out 1690 something. Again, I'm not a historian. This is a very, very rough rough values. This is where you get the laws, the law of gravity. An object is in motion unless acted upon, remains in motion unless acted upon by a force. Force equals mass times acceleration. All those laws are in this Principia. That's the grand thing. And then there's a little appendix. Here's how you do calculus, or rather fluxions. So again, this comes out in 1690s in the UK, in England. Leibniz is working in Germany. He's sort of all over Europe. He's traveling around. So this becomes European mathematics against the islands, as they're called, Great Britain. So Europe has had calculus, and it's been like exploring calculus by lots of people, not just a single individual, for decades before Newton finally publishes what he's been thinking about for those 30 years. And then they get into a big spat. They get into a big argument. The diplomats are brought into this. Like it's not quite World War -1, UK and Germany, but it's something like that. It's a very serious thing where Newton's followers are saying Leibniz stole from Newton, which is a little bit true, and Leibniz's followers saying Newton stole from Leibniz because he published 10 years later. Leibniz's stuff has been available. Newton didn't steal from Leibniz. Leibniz probably independently rediscovered some of this stuff. Neither of them, again, is aware of people like Madhava. Let me write Madhava's name just so he's here. Madhava, in the 1400s, does a bunch of things. See, for me, this is interesting because if not for this fight, like what happened with Madhava? He proved all these amazing things. And then the writings are still there. They survived. They've been passed down. Now modern scientists can go back over and see that it's there, but it didn't spark a revolution. It's very possible that Newton's ideas wouldn't have sparked a revolution either, had Leibniz not come along. And if they hadn't had this fight makes calculus so important. I mean, the ideas of calculus are so important. They make the modern existence as we have it today. But why didn't it happen in India 200 years before? There was nobody sort of, Madhava didn't have a strong enough group around him to bring, one man can only do so much. It's having groups of people around that can all make their own little innovations and grow the subject in completely unexpected ways. That's exactly what Leibniz did by teaching it to the Bernoullis, who taught it to L'Hopital, who taught it to Euler, who taught it to all the rest of us over the centuries. And created this massive science that we now have. If not for this battle, we might still be, we wouldn't have our fancy iPhones and laptops and stuff. Who knows? Who knows? Somehow the world was ready for this fight that took calculus, and calculus never stopped growing from that point on. It had a spurt in Archimedes. It had another big spurt in Madhava, and finally Fermat and Descartes are starting to get into the action. And by the time Newton's there, now we have sort of the complete calculus. Let me show you what the first thing Newton did with calculus as he understood it, and why for the first time we're able to compute pi to lots and lots of decimal places in ways that people couldn't before. So does anybody know how people worked out what pi was before? Has anybody thought about this? Well, what kind of, so this again goes back to Archimedes. Archimedes was the first to give sort of rigorous bounds on pi, and he's the one that proved the formula pi r squared. Pi r squared doesn't make any sense if you start thinking about it. Pi, what is pi? What's the definition of pi? What is it? One more time. It's a random number, no, but what's its definition? It's a ratio of, yes, circumference to diameter, right? Circumference is the ratio of circumference to diameter. Why this number should be the same regardless of it's a small circle or a large circle, that's a beautiful fact of nature of Euclidean geometry. In fact, it's not true on the surface of a sphere where we live. It's not true in hyperbolic space, like our space-time where we live. So this is a fact that actually doesn't ever exist in the real world, but never mind. It's something that's measuring lengths. And yet here it is appearing in an area. Why is pi also the area of a radius 1 circle? That doesn't make any sense. Right? Why is it an area? Because here's what Archimedes does. He says you take this circle, you cut it in half, and then you cut it into all these little pieces like this. And like this. And imagine you sliced it like that, and you open the two pieces up. So if I open this top half up, I'll get all these little triangles, these little pizza slices. I get all these little pizza slices. Okay, you see that? Take this and unroll it. You get all these pizza slices. You do the same thing on the bottom, and you get a whole bunch of other pizza slices. And you stick them together. So you stick them together, and what you get is something that looks like this. And what happens is you slice it thinner and thinner and thinner. Again, Archimedes is really thinking about calculus. Calculus is taking big problems, chopping up into tiny problems where they're easy to solve, and sewing it all back together. Right? That's the big idea. So we've chopped the area of this circle into tiny little pieces. We've put them together like this. And what is so roughly in the limit, as these cuts get smaller and smaller, we're going to get a rectangle. What is the height of the rectangle? How long is each of the pieces? The radius. This is r. Each of these is r. How long is this base of the rectangle? It's half of the circumference. Half of the circumference. So this is circumference over 2. But what is the circumference? The total circumference of a radius r circle? 2 pi r. 2 pi r. It's pi times the diameter. The diameter, right? This is circumference over diameter. So circumference is pi times diameter. So, and diameter is twice the radius. So c over 2 is pi r. That's where pi r squared comes from. He's the one who figured, Archimedes is the one who figured this out. Okay, so people knew that the ratio of circumference to diameter was a constant. They knew that the area of a circle grows quadratically. If you double r, you fourtuple the area. But they didn't know that those constants had anything to do with each other. For all we knew, this could be some constant 3.14, and this could be some other constant 5.39, whatever. The fact that they're the same constant, it's one constant to rule them all. That's Archimedes' discovery. Anyway, so using the area formula, Archimedes managed to go much farther in our understanding of pi than anybody before, because what he started doing is inscribing things like hexagons. He knows how to compute the area of a hexagon with central radius 1, and he would circumscribe hexagons with side length 1, and that sandwiches what pi can be from above and from below. Then he divides that hexagon in half, and makes a 12-gon, and makes a 12-gon, and then a 24-gon, and then a 48-gon, and then 96-gon, and so on. So he does all this like crazy amount of calculation, and this crazy amount of calculation was still being carried out before Newton came to being in Europe. In India, this is Madhava figured out the better way to compute pi. So let me show you. See, we have 10 minutes. I wanted to show you how Newton computed pi. Newton's newfangled computation of pi, also due to Madhava. Again, well, long before Newton. So Newton's messing around with Pascal's triangle. I think maybe this is where we'll. I mentioned something about Newton's binomial theorem. You guys remember Pascal's triangle? Again, Pascal's triangle is something that's been rediscovered by basically any civilization that dared to look at this. There's an old Chinese tablet from I don't remember what era. Anyway, this is something that's been discovered again and again and again. What's Pascal's triangle? Yeah, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. You guys seen this triangle before? What is it representing? Yeah, polynomial coefficients, exactly. If I take 1 plus x squared, that's 1 plus 2x plus x squared. 1, 2, 1. 1, 2, 1. If I take 1 plus x cubed, 1 plus x cubed, that's 1 plus 3x plus 3 squared plus x 1. What's 1 plus x to the 5th? You know how to just read it off? 1, 5, yep, 5 plus 5x, 10x squared plus 15, 10, another 10. Yeah, 10x cubed plus 5x to the 4th plus 1x to the 5th. Okay, you guys have seen these formulas? You know these are also the powers of 11. What's 11 cubed? 1, 3, 3, 1, 11 to the 4th. 1, 4, 6, 4, 1. But that's just because if you put in x equals 10 into these formulas, until you get here, it starts to run over. But until this is just x equals 10 in those formulas. So the power, these are sometimes called the powers of 11. Anyway, so Newton's trying to understand. Newton says, how do I figure out what these coefficients are? Let's look at this formula. 1 plus 5x plus 10x squared plus 10x cubed plus 5x to the 4th plus x to the 5th. He says, here's how we're going to think about this. There's a 1. There's a 5 over 1x. There's a 5 times 4. Maybe you've seen this, binomial coefficients. So the x squared term will have a 2 factorial in the denominator and 5 times 4 in the numerator. And the x cubed term will have a 5 times 4 times 3 over 3 factorial, 3 times 2 times 1, x cubed. And the x to the 4 term will have a 5 times 4 times 3 times 2 over 4 times 3 times 2 times 1. Does that make sense? And if you cancel everything, you get a 5. If you cancel everything here, the 3 cancels, the 2, and I just get 10. And what's the x to the 5 term? 5 times 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1, x to the 5. And what's the x to the 6 term? 5 times 4 times 3 times 2 times 1 times 0 over 6 factorial, x to the 6. So there is no x to the 6th term. It just stops. Does that make sense? So you should think of Pascal's triangle as having zeros all outside of it, sort of implied zeros all around. So here's what Newton does. Newton says, follow this pattern. What about 1 plus x to the negative 1? Can we work that out? Well, I should take 1 plus negative 1 over 1x. Plus, how about this? I should do negative 1 and then 1 less than that, negative 2 times 2 factorial x squared. You see that? And what's the next one? Negative 1, negative 2, negative 3. Negative 1 times negative 2 times negative 3 over 3 factorial x cubed. And here, negative 1, negative 1, negative 2, negative 3, negative 4 over 4 factorial x to the 4th, and so on. What does that come out to? Right. This is a 1 minus x minus minus. This one's plus x squared. How about this one? Minus x cubed plus x to the 4th minus x to the 5th, and so on. That's the same exact formula. If you remember, we had a formula that was 1 plus r squared plus r cubed, and so on, which came out to 1 over 1 minus r. If you set r equal to negative x, Here you get 1 over 1 plus x, which is this. And here you get 1 minus x plus x squared minus x cubed plus x to the fourth, and so on. All right, so that seems to work out. Then he says, wait a second, what if I do this with, what's 1 plus x to the 1/2? Okay, let's try to follow the pattern. 1 plus 1/2 over 1 times x, that's the first term, plus 1/2 times 1 less than that. 1 less than that is negative 1/2 over 2 factorial x squared, plus 1/2 times negative 1/2 times negative 3/2 over 3 factorial x cubed, and so on. Does that make any sense? You see, now we're going to get an infinite sum. Here we also had an infinite sum. We never hit a 0. We never hit a 0 like we would if we started with a positive whole number. So what does this come out to? I get 1 plus 1/2 x, and I get negative 1/8 here, minus 1/8 x squared. How about here? Yeah, it's plus, there's 3 factorial in the denominator. There's a 3 on top. The 3 on top and bottom cancel, and I get a 2, 2, 2, 2. That's 4 2s plus 1/16 x cubed. Hopefully somebody's checking this, and more stuff. Did I get that right? Right. 3 over 8 divided by 6. The 3 cancels. The 6 leaves a 2. 8 times 2, 16. And then now how am I going to check if this formula makes any sense? Right now we're just pattern matching. Well, what happens if I take this quantity and I square it? So let's take this quantity and I square it. Why do I want to see what happens if you square it? If this has any business being called 1 plus x to the 1/2, if I square it, I should get 1 plus x. So let's see. I square it, I get a 1. I'll get an x. What are the x terms? How can I get an x? So I have this times itself. Let me multiply it by itself. 1 plus 1/2 x minus 1/8 x squared plus 1/16 x cubed, and so on. So how do I get an x term? I can do 1 times x, or I can do, 1 times 1/2 x, or 1 times 1/2 x. Well, that's 2 times 1/2 x. So far, so good. How do I get an x squared term? There's this thing times 1. So that's negative 1/8 times x squared. There's this thing times 1. That's another negative 1/8 x squared. There's also 1/2 x times 1/2 x. That's 1/2 squared. That's 1/4 x squared. That's the only way I can get an x squared term. Everybody see that? What's negative 1/8 plus negative 1/8? Negative 1/4 plus 1/4. There's no x squared term. How do I get an x cubed term? I can get a 1/16. Question? Does this make sense? 1/16 x cubed from here and another one from there. So there's 2 of them. I could also do 2 times 1. So there's going to be 2 ways to do 1/2 x times negative 1/8 x squared. And that's the only way I can get an x cubed. I can either take the x cubed, there's 2 ways of doing it, or I can multiply an x by an x squared. And there's 2 ways of doing that. What is that? This is negative 1/8. This is positive 1/8. And they cancel. And then he checks the x to the 4th terms and x to the 5th terms, and they all cancel. Everything cancels. And he gets 1 plus x. So he gets this thing squared to be 1 plus x. So he's happy with this being square root of x. And he tries this for a bunch of other terms. And then, so I'll leave the rest of this as an exercise for you. He says, wait a second, I know how to figure out the area of a circle. A circle is 1 minus x squared to the 1/2. That's this curve. Right? So the area here would be, what's the area? This is a circle of radius 1. Pi over 4. So this area is equal to pi over 4. But this sum, if I multiply all this out, it's the same formula that we already have, 1 plus something to the 1/4, except that something you have to replace by negative x squared. So he gets a series here. He gets some kind of complicated series. I'm just going to make something up. X to the 4th over 2 plus x to the 3/8 or whatever, right? These aren't real numbers. These are fake numbers. And he says, I know what the area under all of those graphs is. So if I add those areas up, I'll get a nice series representing pi over 4. And so he gets a much, much faster way to compute pi than the geometric method that started with Archimedes. All right, something to think about. We will continue with actual calculus in the modern way